To the human eye, the space between the planets appears as a perfect, crystalline void. When we look up at the night sky, we see points of light suspended in a vast, motionless black. We have been conditioned to think of this blackness as an absence of vacuum where nothing exists but gravity and the occasional stray atom. We conceive of the solar system as a collection of lonely, solid marbles rolling around a central fire, separated by millions of kilometers of absolute nothingness. This perception, however, is an illusion born of our biological limitations. If our eyes were tuned to see charged particles instead of visible light, or if we could perceive magnetic fields as we perceive color, the night sky would not be dark at all. It would be a blinding, turbulent fog. The reality of our celestial neighborhood is that it is not empty. It is thick with the atmosphere of the sun. We do not merely orbit the sun, we live inside it. The star at the center of our system is not a static ball of burning gas that simply sits there and shines. It is a violent, churning engine of nuclear fusion that is constantly shedding its own mass, tearing itself apart layer by layer and hurling that material outward in all directions. This continuous radial explosion creates a physical medium that permeates every cubic centimeter of the solar system. We call this phenomenon the solar wind, but the term is somewhat gentle for what it actually is: a supersonic torrent of plasma, a relentless river of electrified gas that rushes past the Earth at speeds varying between 300 and 800 kilometers per second. To understand the journey to the edge of the solar system, one must first appreciate the density and violence of the environment through which that journey takes place. The noise of the sun is physical. It begins in the corona, the tenuous outer atmosphere of the star, where temperatures inexplicably soar to millions of degrees. The heat here is so intense that the sun's gravity can no longer hold on to the energized particles. Protons and electrons boil off the surface, escaping the star's grip and accelerating into the dark. They carry with them the magnetic signature of their birth, a ghostly imprint of the sun's twisting magnetic field, locked into the plasma like a memory. This outflow is constant. There has never been a moment in the 4.5 billion year history of the Earth where this wind has ceased working. It is the dominant weather system of the local universe. When we launch a spacecraft, we are not sending it into a neutral vacuum. We are pushing it upstream against a river of radiation. Every planet, every asteroid, and every comet in the solar system is submerged in this flame. When the wind strikes the magnetic field of the Earth, it compresses it, flattening the sunward side and stretching the night side into a long, trailing tail. The auroras that dance over the poles are merely the visible interaction of this solar breath crashing against our planetary shield. They are the only visual evidence we usually have that we are swimming in a star's exhalation. But as we move further out, the nature of this wind changes. Near the Earth, the solar wind is dense and gusty, reacting violently to solar flares and coronal mass ejections. It is a chaotic, stormy region. However, as the material spreads out over the immense distances to Jupiter, Saturn, and beyond, it creates a massive, inflated structure. This structure is the heliosphere. The term sphere implies a perfect shape, but it is more accurately described as a bubble of Messier cavity carved out of the galaxy by the sheer pressure of the sun's output. Inside this bubble, the laws of the sun apply. The magnetic fields are solar, the particles are solar. The physics are dictated by the central star. This bubble defines the boundaries of our existence. It acts as a cocoon, a sanctuary. The galaxy outside is filled with high-energy, cosmic rays, subatomic shrapnel from supernova explosions and black holes that tear through space at nearly the speed of light. If these galactic rays were allowed to enter our system they would strip away our ozone layer and sterilize the surface of our planet. The solar wind, by inflating the heliosphere, pushes back against this galactic pressure. It creates a shield, a buffer zone that deflects the worst of the interstellar radiation. In a very real sense, the sun protects us from the galaxy. The architecture of this bubble is immense. As the solar wind travels outward, past the orbit of Mars in the asteroid belt, it begins to thin, but it does not slow down. It maintains its supersonic speed, carrying the sun's magnetic field with it. Because the sun rotates once every 27 days, this magnetic field is wound up into a vast, arching spiral, like the waterform of a spinning garden sprinkler. This is known as the Parker spiral. A spacecraft, traveling away from the sun, must navigate the ridges and troughs of this magnetic structure. It is a landscape of invisible hills and valleys, current sheets and magnetic cliffs, all moving outward, always outward, driven by the ceaseless pressure from the center. For decades, astronomers and physicists could only theorize about how fast this wind extended. They knew it could not go on forever. Eventually, the pressure of the solar wind would have to weaken as it spread over a larger and larger volume. They reasoned that there must be a point where the outward force of the sun is finally balanced by the inward pressure of the interstellar medium, the gas and dust that exists between the stars. There had to be a limit to the sun's empire, but predicting where that limit lay was a matter of guesswork. Was it just beyond Jupiter? Did it reach out to the orbit of Pluto? Or did it extend much further into the deep, cold dark where the sun appears as nothing more than a bright star? The only way to find the edge was to go there, to travel until the wind stopped. This required a shift in perspective regarding the machines we built. We tend to think of Voyager as a camera, a robotic photographer sent to capture portraits of the gas giants. And indeed, for the first decade of its life, that was its primary function. It showed us the storms of Jupiter and the rings of Saturn, dazzling the world with the complexity of our planetary neighbors. But once the planets were behind it, the cameras were eventually turned off to save power. The machine became something else. It became a sensor in the dark, a lonely meteorological station drifting through the outer reaches of the solar atmosphere. Its mission shifted from seeing to feeling. It was no longer looking for moons. It was measuring the density of the plasma and the speed of the particles hitting its hull. It was tasting the air, waiting for a change in the flavor of the vacuum. As it drifted past the orbit of Neptune, the silence of the visual spectrum, the lack of planets to photograph, was contrasted by the continuous noise of the particle data. The solar wind was still there, blowing past the craft at supersonic speeds, a persistent hot wind in a deeply frozen landscape. The bubble was larger than anyone had anticipated, year after year. The telemetry confirmed the same reality. The sun was still in charge. The dominance of the solar wind remained absolute, even billions of kilometers from the source. The bubble felt infinite. We began to wonder if the spacecraft would run out of power before it ever reached the boundary. The space we were traversing was monotonous, defined by the same stream of protons and electrons that washes over the Earth, only thinner, colder, and more stretched out. To the sensors of the Voyager probe, the environment was familiar. It was still home. Even if home had become a dark and lonely place, the journey through this outer expanse forces us to confront the sheer scale of the sun's influence. We are accustomed to measuring the solar system by the orbits of the planets, drawing a line at Pluto or the Kuiper Belt and declaring, "This is the end." But physically, the planets are merely debris caught in the inner eddies of the heliosphere. The true solar system is the heliosphere itself, this colossal volume of space filled with solar plasma. To leave the solar system, one does not merely pass the last planet. One must exit the atmosphere of the star. This atmosphere is a dynamic, living structure. The bubble does not maintain a static shape or a constant size. It breathes. As the sun moves through its 11-year cycle of magnetic activity, the intensity of the solar wind fluctuates. During periods of solar maximum, when the face of the star is pockmarked with sunspots and the magnetic storms are most violent, the wind blows harder and denser. The pressure inside the heliosphere rises, and the entire bubble expands, pushing outward into the galaxy like a lung inflating with a deep breath. Conversely, during the solar minimum, the wind calms, the pressure drops, and the bubble contracts, yielding ground to the crushing weight of the interstellar medium. The boundary of our world is therefore not a fixed line on a map, but a shifting frontier, pulsing in time with the rhythm of the star at its center. This rhythmic expansion and contraction highlights the delicate balance that sustains our local reality. We exist in a state of pressurized equilibrium. The only reason the solar system exists as a protected enclave is that the sun pushes back against the galaxy with sufficient force. Outside the bubble, the pressure of the interstellar clouds, dense, cold, and heavy, is constantly trying to collapse our sanctuary. Without the solar wind to hold back this tide, the heliosphere would implode, and the harsh environment of the galactic void would flood the inner solar system. The radiation environment of Earth would change drastically, and the history of life on our planet might have been fundamentally different. We are, in effect, living inside a cavity inflated by starlight and plasma, held open against the crushing dark by the sheer stubbornness of the sun's outflow. Within this cavity, the noise is incessant to the sensitive instruments of a spacecraft. The heliosphere is a raucous place. The solar wind is turbulent, filled with eddies and swirls of magnetized plasma. Shock waves from coronal mass ejections ripple through the system like tsunamis in an ocean, crashing against the planets and reverberating all the way to the edge of the bubble. This magnetic turbulence creates a chaotic background static, a constant chatter of charged particles interacting with magnetic field lines. For decades, Voyager listened to this familiar roar. It was the sound of home. It was the signature of the sun's dominance, a frequency that defined the environment. For billions of kilometers in every direction, the expectation was that this noise would eventually fade, that the wind would gently die away as the spacecraft traveled further from the source. But the transition from the vast solar system to the galaxy is not a gentle fading. The physics of the boundary dictate a more violent confrontation. Because the solar wind travels at supersonic speeds, it cannot simply dissipate into the interstellar medium. It must crash into it. When a supersonic flow encounters an obstacle, in this case, the wall of interstellar gas, it creates a shock wave. This is the termination shock, a standing wave of immense proportions, where the solar wind is abruptly slowed from supersonic to subsonic speeds. It is a wall of compression, a turbulent, heated region where the smooth flow of the star's atmosphere piles up against the resistance of the galaxy. We knew this barrier existed. We knew that somewhere, out in the darkness, the wind had to stop. But because we lived deep inside the gravity well of the sun, close to the warmth and the light, the edge felt abstract, almost theoretical. It was a line drawn in equations, not a physical place one could visit. For most of the space age, our exploration was confined to the shoreline of the cosmic ocean. The Moon, Mars, Venus, even the grand tours of the outer planets were merely excursions within the harbor. We had never sent a ship to the open sea. We had never tested the strength of the hull against the true pressure of the deep. The launch of Voyager marked the beginning of that test. It was an act of hurling a bottle into the dark to see where the water changed. As the spacecraft drifted silently through the decades, moving past the orbits of the giants and into the quiet void beyond, it was slowly climbing the slope of the solar system's pressure hill. It was ascending out of the valley of the sun's influence. The journey was not just about distance. It was about a machine designed by humans, built with 1970s technology, surviving long enough to reach a frontier that no eye had ever seen. The significance of reaching this edge cannot be overstated. Throughout human history, every frontier we have crossed has been a terrestrial one, an ocean, a mountain range, a continent. These were boundaries within a single biosphere. Crossing the Heliosphere, final boundary of the Heliosphere, would be different. It would be the first time a human object left the native environment of its origin. It would be an exit from the atmospheric system that birthed us. It is the difference between stepping out of a house and stepping off the planet. As Voyager continued its silent cruise, the data it returned began to hint at the approach of this final threshold. The texture of the space around it began to change. The wind became erratic. The smooth, radial flow of particles from the sun started to stagnate, turning sideways, as if the river was hitting a wall and spreading out. The noise of the magnetic field grew confused. These were the first tremors of the edge. The spacecraft was entering the transition zone, the turbulent shoreline where the solar tide meets the galactic ocean. It was no longer deep inside the comfortable bubble. It was pressing against the skin. We often speak of the emptiness of space, but the data from Voyager revealed that there is no such thing as empty space. There is only territory. And the territory of the sun was coming to an end. The familiar physic, the familiar radiation, the familiar window of it was about to be left behind. The head lay a domain ruled by different forces, different stars, and a silence so profound it would challenge our understanding of what it means to be isolated. The probe was poised to cross the most significant border in the history of exploration, moving from the noise of our own campfire into the absolute, crushing quiet of the wild night. To understand where Voyager has gone, we must first abandon the tools we use to measure the world around us. Kilometers and miles are terrestrial inventions, units derived from the curvature of our planet and the length of a human stride. They are adequate for mapping continents or measuring the flight of an airplane, but when applied to the outer dark, they lose their meaning. the numbers become so large that the human mind can no longer hold them. To say that a spacecraft is 24 billion kilometers away is to state a fact that feels abstract, almost mathematical, rather than physical. At this scale, distance ceases to be a measurement of space and becomes a measurement of time. In the deep solar system, the only ruler that matters is the speed of light. We perceive light as instantaneous. When we flip a switch, the room illuminates immediately. When we speak to someone on the other side of the world, the signal travels through fiber optic cables so fast that the conversation feels seamless. But light has a finite speed limit, 300,000 kilometers per second. It is fast, but it is not infinite. On the scale of the cosmos, light is actually quite slow. It crawls. To map the isolation of the Voyager probe, we must visualize the universe not as a static picture, but as a system defined by the delay of information. Consider the journey of a radio command sent from Earth. When a flight controller in California types a sequence of instructions to adjust a heater or toggle a sensor, that command leaves the dish at the speed of light. In 1 second, it passes the Moon. In 4 minutes, it passes the orbit of Mars. It takes over an hour to reach Jupiter, and nearly an hour and a half to reach Saturn. But to reach the edge of the Heliosphere, the signal must travel for nearly an entire day. It races through the vacuum for 22 hours, crossing billions of kilometers of silence, before it finally washes over the antenna of the spacecraft. This delay creates a profound disconnect between the creators and the creation. Voyager does not exist in our present moment. The machine we see in our mind's eye, the gold-plated dish, the boom arms, the sensors is actually a ghost from the past. When we receive data from Voyager, we are not seeing what is happening now. We are seeing what happened yesterday. If the spacecraft were to collide with debris or suffer a catastrophic failure, it would continue to transmit its steady heartbeat of data for another 22 hours before the silence reached Earth. We would be watching a machine that was already dead, unaware that the mission had ended a day ago. We are forever chasing its shadow, locked in a permanent temporal lag that no technology can bridge. This reality transforms the nature of mission control. There is no joystick, no real-time piloting. Driving Voyager is like steering a ship on an ocean where the rudder takes a day to respond to the wheel. Every command is a bottle cast into the dark, sent with the hope that it will be received and understood. The flight team lives in a state of perpetual anticipation. They send a query, and then they must wait nearly 2 full days for the round-trip confirmation. They go home, sleep, eat breakfast, and return to the console, and only then does the faint whisper of a reply arrive. The conversation is slow, deliberate, and agonizingly quiet. The silence is amplified by the sheer weakness of the signal. As the spacecraft moves further away, the energy of its transmission spreads out, diluting. With every kilometer, by the time the radio beam from Voyager reaches Earth, it has spread so wide and become so faint that it possesses less energy than a falling snowflake landing on the ground. It is a billionth of a watt. To hear this whisper requires the largest, most sensitive ears humanity has ever built. The deep space network. These massive parabolic dishes, located in the deserts of California, the scrublands of Australia, and the hills of Spain, are constantly turning, tracking the faint pinprick of the probe against the background of the stars. The Earth rotates, and as one station loses the signal below the horizon, another on the opposite side of the globe must pick it up. It is a continuous, global relay race to maintain the connection. If we were to stop listening, even for a moment, the spacecraft would vanish. It would not physically disappear, but it would cease to exist in our reality. It requires a constant, active effort of human will to keep the line open. This fragility highlights the immense scale of the void Voyager is traversing. Between the planets, there are waypoints, landmarks that give the mind a sense of progression. We can visualize the distance from Earth to Mars, or Mars to Jupiter. But beyond Neptune, there are no landmarks. There is only the Kuiper Belt, a sparsely populated ring of frozen debris, and then the abyss. For the last 30 years, Voyager has been flying through a featureless expanse. There are no passing asteroids to photograph, no giant moons to analyze. There is only the black texture of the empty solar system and the slow tick of the cosmic ray counters. In this region, the sun is no longer a blinding disk that dominates the sky. It has shrunk to a brilliant, piercing star, brighter than the others, but too small to show a disk to the naked eye. The daylight here is dim, resembling a perpetual twilight. If you were floating next to the spacecraft, you would be bathed in a cold, grey illumination, sharp enough to cast shadows, but lacking the warmth we associate with our home star. The darkness is the dominant feature. It presses in from every side, a sphere of night that encompasses the entire field of view. The isolation of the machine is total. It was built by hands that are now aged or passed away. The software running in its computer is written in languages that are no longer taught in universities. It operates on memory capacity smaller than that of a modern car key fob. Yet, this primitive explorer is the furthest object our species has ever touched. It is a tiny, geometric assembly of aluminum and beryllium, humming quietly to itself in a place where temperature is measured in single digits above absolute zero dot. As it drifts, the concept of here and there dissolves. On Earth, we are anchored by the horizon. We know where we are relative to the mountains, the sea, or the city limits. In the outer heliosphere, there is no horizon. There is no up or down, no north or south. There is only the vector of the spacecraft's momentum and the position of the guide stars locked in its optical sensors. Voyager navigates by fixing its gaze on Canopus, a bright star in the southern constellation of Carina. It uses this star as an anchor, a lighthouse, to keep its antenna pointed back toward the invisible speck of Earth. If it were to lose this lock, if it were to drift even slightly off axis, the beam would miss our planet entirely, and the connection would be severed forever. The journey has thus become a balancing act of extreme precision, played out over extreme distances. We are holding a thread that spans the solar system, a thread that has grown thinner and more fragile with every passing year. The tension on this thread is not physical, but intellectual. It is the tension of knowing that the object at the other end is moving deeper into a territory we cannot see, cannot touch, and can barely comprehend. We are tethered to a machine that is slowly leaving the realm of human experience. This vast separation creates a unique form of solitude for the spacecraft. It is not merely alone in space, it is alone in time. The particles it encounters, the magnetic fields it measures, these are local phenomena that happen in the solitude of the deep heliosphere, unwitnessed by any other observer. When Voyager records a spike in cosmic rays, it is the sole witness to that event. By the time the data reaches us, the event has long passed, the particles have dissipated, and the region of space where it happened is millions of kilometers behind the craft. We are not watching the exploration. We are reading the diary of a traveler who is always a day ahead of us, describing a path that closes up as soon as it is walked. The sheer volume of space involved is difficult to convey with analogies, but we must try. If the sun were the size of a grapefruit placed in the center of a city, the Earth would be a grain of sand 10 meters away. Jupiter would be a marble a block down the street. But Voyager would be kilometers away, far outside the city limits, drifting through the dark countryside where the streetlights have long since faded. And yet, despite this immense gap, it is still within the yard of the sun. The distance is not just empty space. It is a volume filled with the history of the sun's emissions, a record of solar storms and magnetic upheavals that have washed past the craft over the decades. To understand the silence at the edge, we must first understand the nature of the noise at the center. We often conceive of the sun as a static perfect, glowing sphere of yellow light that sits motionless in the dark, radiating heat like a campfire. But this image captures only a fraction of the star's true nature. The sun is not merely a lamp, it is a fountain. It is a continuously erupting engine that does not just emit light, but physically sheds its own body into the void. It is constantly exhaling, and this exhalation creates a physical atmosphere that extends far beyond the orbits of the planets. This atmosphere is not made of air, it is made of plasma, the fourth state of matter. On Earth, we are accustomed to solids, liquids, and gaseous states defined by how tightly atoms are bound to one another. But in the extreme violence of the sun, atoms cannot hold themselves together. The heat is so intense that electrons are stripped from their nuclei, creating a soup of free-floating negative charges and positive ions. This ionized gaseous plasma behaves unlike anything in our daily experience. It is electrically conductive, highly reactive, and, most importantly, it is coupled to magnetic fields. It does not just flow, it writhes. It carries the magnetic signature of the sun with it, locking the star's influence into the very fabric of the material it ejects. The origin of this flow lies in the corona, the sun's tenuous outer atmosphere. Here, a mystery of physics plays out that drives the entire solar system. While the surface of the sun is a blistering 6,000 degrees Celsius, the atmosphere above it, the corona, inexplicably soars to temperatures of over 1,000,000 degrees. It is a region of unimaginable energy, where particles are agitated into a frenzy of motion. The thermal pressure in this layer becomes so great that the sun's immense gravity can no longer contain it. The atmosphere simply boils over. It expands outward, not as a gentle breeze, but as a violent, supersonic explosion that never ends. This is the solar wind. Supersonic in this context refers to the speed of information within the medium. In any fluid, whether it is the air in a room or the plasma in space, sound waves represent the speed at which pressure changes can communicate. If you clap your hands, the pressure wave moves at the speed of sound. If an object moves faster than sound, the air ahead of it receives no warning that the object is coming. The solar wind accelerates so rapidly as it leaves the sun that it quickly exceeds the speed of sound within the plasma. By the time it passes the Earth, it is traveling at hundreds of kilometers per second, thousands of times faster than a hurricane. It creates a flow where the information cannot travel upstream. The plasma at the edge of the system cannot tell the plasma at the sun that it is hitting an obstacle. The wind simply keeps coming, blind and deaf to what lies ahead, driven by the relentless thermal engine at the core. This wind creates a tangible, physical pressure. We do not feel it on Earth because our planet is shielded by its own magnetic field, which deflects the flow like a rock parting a stream. But out in the open void, the pressure is undeniable. If you were to unfurl a giant, reflective sail in deep space, the impact of these particles would physically push you. It is a tenuous force spread over a vast area, but it is constant. Over millions of kilometers, this pressure accumulates, clearing out the debris of the galaxy. It sweeps the solar system clean, pushing away the interstellar dust and gas that tries to drift in. We must visualize this not as empty space, but as a pressurized volume. Think of a balloon being inflated inside a swimming pool. The pool represents the interstellar medium, the heavy, dense material of the galaxy. The air inside the balloon represents the solar wind. As the sun breathes out, it inflates the balloon. The skin of the balloon is the boundary where the two pressures meet. The stronger the sun blows, the larger the balloon becomes, pushing back the heavy water of the galaxy. If the sun were to suddenly stop blowing, the weight of the galactic water would crush the bubble, collapsing the heliosphere down to a fraction of its size. The structural integrity of our solar system therefore relies on this dynamic balance. We are living inside a bubble of low density, a high-temperature plasma that is carving out a cavity in a region of high-density, low-temperature galactic material. The wall of our house is built entirely of pressure. It is a wall made of the momentum of protons and electrons, refusing to yield to the outside. This is why the wind is the defining feature of the heliosphere. It is the architectural support beam that holds the roof up. Without the kinetic energy of these particles, the protective domain of the sun would cease to exist. As the wind travels outward, it undergoes a transformation. Near the sun, it is dense and hot. But as it expands into the vast volume of the outer solar system, it spreads out. By the time it reaches the orbit of Saturn or Uranus, the density has dropped dramatically. There may be only a handful of protons in a space the size of a sugar cube. Yet, the speed remains. The momentum remains. The particles are like bullets, fired in a vacuum. They do not slow down simply because they have traveled far. They coast at supersonic velocities, preserving the energy of their birth in the corona. This means that even at the edge of the system, billions of kilometers from the source, the wind still possesses the power to push. It is a thin, ghostly wind, but it is moving with tremendous force. This flow is complicated by the rotation of the sun. Because the sun spins, it does not shoot plasma out in straight lines like spokes on a wheel. Instead, it sprays the solar wind out like a garden sprinkler. The magnetic field lines rooted in the sun's surface are dragged out into the deep system, twisting into a massive Archimedean spiral. A particle leaving the sun travels radially outward, but the magnetic field line it is attached to curves behind it. This creates a magnetic tension, a coiled spring that fills the entire heliosphere. This frozen influx is a crucial part of the pressure. The solar wind is not just throwing rocks. It is throwing magnetized webs. When this magnetized wind hits the boundary of the system, it doesn't just impact, it interacts electromagnetically. Journey of a single particle in this wind is a lonely odyssey. It leaves the chaotic inferno of the sun. It accelerates past the rocky inner planets in a matter of minutes, and then spends months or years drifting through the dark gap between the gas giants. It flies past Jupiter, perhaps getting a gravitational kick or a magnetic twist, and continues into the unknown. For decades, it travels without hitting anything. The solitude is absolute, but eventually, it must encounter the end of the line. It must reach the point where the push of the sun is no longer strong enough to shove the galaxy aside. This point of interaction is governed by the laws of fluid dynamics. Because the wind is supersonic, it cannot gradually slow down as it approaches. The obstacle: supersonic flows do not decelerate smoothly. They crash. They undergo a catastrophic transition known as a shock. Just as a supersonic jet creates a sonic boom when it plows through the air, the solar wind creates a massive, standing shockwave when it senses the pressure of the galaxy. This is the termination shock. It is the first line of defense, the point where the solar wind slams on the brakes. At this shock front, the orderly high-speed flow of the wind is instantly shattered. The kinetic energy of the speeding particles is converted into heat. The plasma is compressed, slowed down to some speeds, and heated up to hundreds of thousands of degrees. It is a chaotic, turbulent wall of fire in the deep cold of space, where the sound of the wind changes. It goes from a silent, smooth, supersonic stream to a noisy, subsonic riot of particles. This is the transition zone. Before this point, the wind rules. After this point, the wind is struggling, fighting a losing battle against the encroaching pressure of the interstellar medium. On February 14, 1990, the Voyager 1 spacecraft commanded its cameras to turn back toward the center of the solar system, snapped a final mosaic of images, including the famous pale blue dot, and then, 34 minutes later, shut its eyes forever. The cameras were powered down to save energy and memory for the long darkness ahead. For the general public, this moment marked the end of the mission's visual legacy. There would be no more postcards from the giants, no more swirls of Jovian clouds or rings of Saturnian ice. To the human eye, the probe had gone blind. But to the scientists who built it, Voyager was not going blind. It was simply closing its eyes to focus on its other senses. It was shifting its attention from the visible spectacle of the planets to the invisible texture of the void. To understand how we found the edge of the solar system, we must understand that the boundary is not a visual phenomenon. There is no line painted in space, no sudden change in the color of the darkness. If you were looking out a window on the spacecraft, the moment of crossing would look exactly the same as the moment before. The stars would not shift. Sun would remain a piercing point of light. The transition is purely physical and electromagnetic. It is a change in pressure, density, and magnetic orientation. To detect such a change requires instruments that function less like eyes and more like skin and ears. It requires a machine capable of feeling the environment. Voyager 1 is equipped with a suite of these tactile sensors, instruments designed to touch the medium through which it travels. The most critical of these for the interstellar phase is the plasma wave subsystem. Physically, this instrument is the most prominent feature of the spacecraft, though it is often mistaken for structural struts. It consists of two long and booms extending outward in a V shape from the main body of the craft. Each boom is 10 meters long, unfolding like a carpenter's ruler. Together, they form a dipole antenna spanning 20 meters, sensitive enough to detect minute fluctuations in the electric field of the surrounding gas. In the vacuum of space, these antennas act as the spacecraft's ears. They are listening for the vibration of the plasma. Because the solar wind and the interstellar medium are ionized gases, they can carry waves just as air carries sound. When electrons in the plasma oscillate, they create electric field ripples. The long antennas of the plasma wave subsystem detect these ripples as voltage differences between the two booms. The instrument then converts these electrical signals into frequencies that fall within the range of human hearing, from a few hundred hertz up to several kilohertz. If you were to plug the output of this instrument into a speaker, you would hear the solar system. You would hear the whistles of lightning from Jupiter, the roar of the solar wind, and the sharp cracks of dust impacts. This instrument allowed Voyager to hear the density of the space around it. a capability that would become the ultimate arbiter of its location. Complementing this sense of hearing is the cosmic ray subsystem. If the plasma antennas are the ears, the cosmic ray subsystem is the skin, sensitive to the rain of high-energy particles. This instrument does not look for waves, it looks for bullets. It consists of a stack of solid-state detector silicon wafers and scintillators that register a pulse whenever a charged particle punches through them. Its job is to count. It sits in the dark, ticking away, cataloging every proton and heavy ion that strikes the hull. This instrument provides the crucial context for the journey. It distinguishes between two distinct populations of particles, those born in the Sun and those born in the galaxy. The solar particles are relatively slow and low energy, carried outward by the solar wind. The galactic particles are the cosmic rays protons, accelerated to near-light speeds by supernova and other violent events deep in the Milky Way, inside the heliosphere. The solar wind acts as a shield, keeping the count of galactic cosmic rays low. Outside, in the open ocean of interstellar space, the galactic count should skyrocket. The cosmic ray subsystem was the watchman looking for this specific inversion. The moment the solar count dropped to zero and the galactic count spiked. Operating these instruments requires a level of patience and ingenuity that borders on the miraculous. Voyager is not a modern machine. It was designed in the early 1970s, an era when computers filled entire rooms and data was stored on magnetic tape. The brain of the spacecraft is a computer system with less than 70 kilobytes of memory, millions of times less than a modern smartphone. It has no hard drive. It processes instructions using a custom-built language that few people alive today can still read. Yet this primitive architecture has proven to be incredibly robust. It is a testament to the philosophy of simplicity. Because it has so few moving parts and so little code, there is very little that can go wrong. However, the greatest challenge facing the ancient observer is not its computing power, but its metabolism. Voyager runs on a nuclear heartbeat. Hanging off the side of the craft is a canister containing spheres of plutonium-238. Its radioactive isotope is unstable. It naturally decays, releasing heat as it breaks down. That heat is converted into electricity it is a battery that can never be recharged, and which inevitably grows weaker with every passing second. At launch in 1977, the generators produced 470 watts of power. Today, they produce barely enough to power a standard light bulb. This decaying energy supply has forced mission controllers into a decades-long game of triage. To keep the ears listening, other parts of the body had to be sacrificed. First, the scan platform that aimed the cameras was shut down. Then, the heaters that kept the propellant lines warm were turned off, allowing parts of the fuel system to freeze. One by one, non-essential instruments, the ultraviolet spectrometer, the planetary radio astronomy instrument, were powered off to conserve the dwindling watts. The spacecraft is slowly freezing to death, prioritizing its core sensors over its extremities. It is a shivering sentinel, wrapping its remaining warmth around the plasma wave and cosmic ray instruments, keeping them alive at the expense of everything else. The data that comes back from these surviving instruments is faint, a trickle of binary code that must cross the immense gap to Earth. The signal strength is so low that the Deep Space Network must use its largest 70-meter antennas to catch it. And even then, the data rate is agonizingly slow, 160 bits per second. This is not a broadband stream, it is a telegraph. The information arrives in a steady, rhythmic drip. A slight rise in the count of galactic protons takes hours to confirm. A shift in the plasma frequency is a data point that must be extracted from the background noise with mathematical precision. There is a profound intimacy in the relationship between the engineers on Earth and this distant machine. They know the quirks of its aging hardware. They know that the tape recorder, a literal reel-to-reel device, has a tendency to stick. They know that the thrusters used to keep the antenna pointed at Earth are degrading, requiring shorter and shorter puffs of gas to maintain stability. They monitor the temperature of every subsystem, watching as the craft cools down by fractions of a degree each year. They are nursing a geriatric explorer, coaxing it to stay awake just a little longer, just until it crosses the line. This constant monitoring creates a unique psychological state. The scientists are not looking for a dramatic image to appear on a screen. They are watching trend lines on a graph. They are looking for a break in the pattern. For years, the graphs were flat lines or gentle slopes, indicating more of the same. The solar wind blew, the cosmic rays were suppressed, the magnetic field spiraled. It was the monotony of the known. But the expectation of the unknown hung over every transmission. They knew the boundary was out there. They knew that at some point, the physics had to break. The anticipation turned every glitch, every dropout, every sudden spike in the data into a potential historic moment. Was that it? Did we just cross? Or was it just a solar flare? In this way, Voyager became more than a robot. It became a proxy for human sensory experience in a place where no human could survive. Its gold-plated chassis, drifting in the absolute cold, was our skin. Its dipole antennas were our eardrums. We were projecting our consciousness into a machine, waiting for it to tell us that the air had changed. The silence of the void was not empty. It was waiting to be heard, but it could only be heard by a machine that had been stripped of its sight and stripped of its warmth, and left with nothing but the raw capacity to detect the vibration of the universe. By the summer of 2012, the wait had become a routine of decades. The Voyager mission had long since transitioned from a sprint past the planets to a marathon through the dark. For the scientists at the Jet Propulsion Laboratory, the daily telemetry reports were remarkably consistent, often monotonous. The spacecraft was drifting through the Heliosphere, the turbulent outer layer of the solar bubble, where the solar wind slows down and piles up. For 7 years, the environment had been a confused, stagnant wash of plasma, like a thick fog that refused to lift. The particle counts remained high, the magnetic fields remained disorderly, and the noise of the sun was a constant, steady roar in the data. There was no indication that the edge was imminent. The models suggested the boundary might still be years away, perhaps not to be crossed until 2015 or even 2020. The probe was simply swimming through the deep, muddy water of the outer system. But in May of that year, the monotony broke. The steady hum of the solar wind data suddenly became erratic. For a few days, the count of solar particles dropped significantly, only to surge back up again. It was a tremor, a warning shot. Then, in late July, it happened again, deeper and more prolonged. The environment around the spacecraft was becoming unstable. It was as if Voyager was a ship sailing out of a harbor, suddenly hitting the rough, choppy waves that marked the transition to the open sea. The boundary was not a static wall. It was a dynamic, shifting surf. The solar system was breathing in and out, washing over the spacecraft and then retreating, leaving it briefly exposed to the galaxy before swallowing it back up. Throughout August, the data became violent. The smooth lines on the graphs turned into jagged spikes and deep valleys. The weather in the deep heliosphere had turned stormy. The science team watched in real time, or rather, with a 20-hour delay that reality imposed as the probe seemed to be surfing along the edge of a cliff. One day, it was clearly inside the sun's domain. The next, it was dangling over the precipice. This was not the clean, mathematical crossing that physicists had drawn on chalkboards for 40 years. It was messy. It suggested that the helium was not a rigid shell, but a complex, permeable membrane that flapped in the cosmic breeze. Then came the 25th of August. On Earth, it was a quiet Saturday. The data packets that arrived at the Deep Space Network tracking stations looked, at first glance, like just another set of numbers in the stream. But when the team began to unpack the telemetry from the cosmic ray subsystem, they saw something that stopped them cold. The chaos of the previous weeks had vanished. The jagged fluctuations had flattened out into a sudden, terrifyingly straight line. The count of solar protons, the charged particles that had surrounded the spacecraft every second of every day since it launched in 1977, had dropped. They didn't just decline, they plummeted. Within a span of hours, the intensity of the solar wind fell by a factor of 1,000. It was a collapse. It was as if a switch had been flipped. For 35 years, the spacecraft had been flying through a continuous rainstorm of solar material. On that day, the rain simply stopped. The gauge went to near zero. The familiar atmosphere of the sun, which had been the craft's companion for billions of kilometers, was gone. Simultaneously, the other side of the equation balanced with chilling precision. As the solar particles vanished, the count of galactic cosmic rays, the high-energy subatomic debris from the rest of the universe, spiked. In the same window of time that the solar wind disappeared, the galactic radiation jumped by nearly 10%. The pressure pushing against the hull had swapped. The warm, low-energy push of the sun was replaced by the cold, high-energy bombardment of the galaxy. The spacecraft had stepped out of the shelter. The abruptness of the event was shocking. Nature rarely moves in right angles. In the vast, fluid dynamics of space, changes usually happen over gradients of millions of kilometers. But here was a boundary that was razor-sharp. Voyager 1, traveling at 17 kilometers per second, had crossed the line in less time than it takes to commute to work. It had slipped from one universe into another. The physical reality of the environment had inverted. The magnetic highway. It had been following lead off the map, dropping it into a region where the sun was no longer the dominant source of matter. Back in California, the reaction was not immediate celebration, but deep, scientific anxiety. The data was too clean, too binary. It looked impossible. The team stared at the graphs, searching for an alternative explanation. Was it a malfunction? Had the instrument failed? Was this just another temporary bubble, a magnetic eddy that had temporarily blocked the solar wind? The skepticism was rooted in a specific missing piece of evidence: the magnetic field direction. According to the theoretical models developed over decades, leaving the solar system should come with a compass change. The magnetic field lines inside the heliosphere spiral, east to west, driven by the sun's rotation. The magnetic field lines of the interstellar medium were expected to be oriented differently, perhaps north to south aligned with the galactic plane. If Voyager had truly crossed the boundary, the direction of the magnetic field should have shifted abruptly, but the magnetometer on board reported no such shift. The strength of the field had increased, compressing tighter, but the direction remained exactly the same. This contradiction created a crisis of interpretation. The particle data set out, but the magnetic data set in. How could the spacecraft be bathed in galactic rays and free of solar wind, yet still be locked in the sun's magnetic orientation? The team was paralyzed by the ambiguity. To declare that humanity had left the solar system was a historic claim, one that could only be made once. If they were wrong, if Voyager was merely inside a large, magnetic bubble within the heliosheath, they would lose their credibility. So they waited. They kept the champagne corked. They watched the stream for days, then weeks, then months. They were looking for the solar wind to return, for the rain to start falling again. They expected the boundary to wash back over the spacecraft as the heliosphere breathed out, but the silence held. September passed. October passed. The solar particle count remained flat at the bottom of the graph. The galactic ray count remained locked at the high plateau. The spacecraft was flying through a new, stable regime. The tension in the science community grew. Papers were written and rewritten. Arguments broke out in conference rooms. The Helioclif event, as it came to be known, was undeniably real, but its meaning was fiercely debated. Was this the or was it a magnetic highway? A strange precursor region where the particles could escape but the magnetic field was still solar. The definition of the boundary itself was on trial. Was the solar system defined by its matter or by its magnetism? For the spacecraft, these human debates were irrelevant. It was no longer struggling through the turbulence. The chaotic buffet of the summit was over. It had entered a region of profound calm. The plasma environment was smooth, cold, and dense. The wind had ceased. There was no more flow, no more gusts. Voyager was no longer sailing. It was drifting through a still ocean. The violence of the termination shock and the turbulence of the heliosheath were behind it. It was floating in the dark, motionless relative to the flow of the gas, surrounded by a stillness it had never known. This stillness was the primary characteristic of the new world. For the first time in its life, Voyager was not being pushed by the star that made it. It was coasting. The lack of solar wind noise and the lower frequencies of the plasma wave detector was conspicuous. The background roar had cut out. In its place, there was nothing but a flat, baseline static. It was the electronic equivalent of stepping out of a noisy factory into a snowy field at night. The sudden absence of the sun's breath was more deafening than the noise had been. As 2012 turned into 2013, the realization slowly solidified. The temporary drop was not temporary. The probe was not coming back. The data continued to trace perfectly flat lines. The sun's influence over the particle environment had ended on that specific day in August. The day the wind stopped had marked a permanent transition. We had passed the point of no return without fully realizing it. We were looking at the rear-view mirror, watching the solar system recede, waiting for a signpost we had already passed. The mystery of the magnetic field remained, a stubborn puzzle piece that didn't fit, but the weight of the particle evidence was becoming overwhelming. The spacecraft was immersed in the material of the galaxy. It was touching atoms that had never been inside the solar system. It was being struck by cosmic rays that had traveled unimpeded for thousands of light. Whether the magnetic door had opened or not, the air was different. The taste of the vacuum had changed. When Voyager pierced the skin of the heliosphere, it did not emerge into a vacuum of absolute nothingness. It emerged into a sea. We have conditioned ourselves to think of the space between the stars as a void, a clean, sterile gap that separates the islands of light. But this is a misconception, born of our limited vision. The galaxy is not empty. It is filled with a permeating, tenuous fluid known as the interstellar medium. This medium is the atmosphere of the Milky Way, a vast, continuous ocean of gas and dust that connects every star system to every other. To leave the solar system is not to step into the abyss. It is to wade out into the deep water that surrounds our island. The substance of this ocean is the wreckage of the past. The atoms that Voyager is now drifting through are not fresh creations. They are the ancient exort of dead stars. When a star reaches the end of its life, whether it puffs off its outer layers in a gentle planetary nebula or tears itself apart in a supernova, it returns its mass to the galaxy. It seeds the dark with carbon, oxygen, iron, and silicon. Over billions of years, these elements mix with the primordial hydrogen left over from the Big Bang, forming great, drifting clouds. The empty space Voyager traverses is actually a graveyard of celestial history, a suspension of particulate matter that once burned in the hearts of suns that went dark long before the Earth was born. The most profound revelation that came with crossing the boundary was the realization of just how different this galactic environment is from our own. Inside the heliosphere, we are accustomed to the solar wind, a medium that is hot, fast, and incredibly thin. The wind from the sun is tenuous, a rarefied breath that screams outward at supersonic speeds. But the interstellar medium is the opposite. It is cold, slow, and remarkably dense. By dense, we speak in relative terms. It is still a vacuum, better than any we can create in a laboratory on Earth. But compared to the interior of the solar bubble, it is thick. Upon crossing the threshold, Voyager detected a dramatic shift in the texture of space. The density of the electrons around the spacecraft jumped by a factor of 40. This was a staggering increase. It forced scientists to completely re-evaluate our place in the cosmos. We realized that our solar system is effectively a low-density cavity, a bubble of hot, thin gas carved out of a much colder, denser galactic cloud. We are living in a rarefied pocket, a hole in the Swiss cheese of the galaxy. The sun, through the sheer force of its wind, keeps this heavy cloud at bay, preventing it from crushing in and flooding the planetary system. The temperature of this outer ocean creates a paradox of physics. The solar wind Voyager left behind was hot, with particle temperatures in the tens of thousands of degrees, yet it was so thin it transferred almost no heat. The interstellar medium, by contrast, is cold, with temperatures hovering around 6,000 degrees, comparable to the surface of the sun. But cliff by cosmic plasma standards, yet, because it is so much denser, it exerts a much greater pressure. It is a heavy, sluggish environment. The material here is not rushing outward in a radial wind. It is drifting, swirling slowly in currents that span light. It is a calm, viscous fluid compared to the chaotic storm of the solar wind. This particular region of the ocean has a name: the local interstellar cloud. It is a wisp of galactic fog, roughly 30 light-years across, and our sun has been moving through it for the last 40,000 years. It is a cloud only in the astronomical sense. If you were inside it, you would not see it with your eyes. The stars would still look clear and sharp, but to a particle detector, or to the magnetic sensors of a spacecraft, the cloud is a tangible physical structure. It is composed of hydrogen and helium atoms, some ionized, some neutral, mixed with microscopic grains of dust silicates and carbon soot that are smaller than the particles in cigarette smoke. As Voyager moves deeper into this cloud, it is essentially sampling the weather of the galaxy. This weather is driven not by a single star, but by the collective breathing of the entire Milky Way. Supernova that explode hundreds of light-years away send shockwaves rippling through this medium. compressing the gas and creating turbulence that can last for millions of years. The magnetic fields here are not the neat, spiraling lines of the sun. They are smooth, draped ribbons that stretch across the cosmos, aligned by the rotation of the galactic disk. They are the ley lines of the galaxy, guiding the flow of cosmic rays and shaping the structure of the clouds. Their transition into this medium marked a shift in the spacecraft's experience of motion. Inside the solar system, movement is defined by orbits. Everything is falling around the sun. But in the interstellar medium, motion is defined by drift. The gas Voyager is passing through is not orbiting our sun. It is orbiting the center of the galaxy, taking 200 million years to complete a circuit. There is a serene heaviness to this new environment. The turbulence of the Heliosphere, that jagged, stormy region where the solar wind piled up, is gone. The plasma here is laminar, meaning it flows in smooth, parallel layers without disruption. The magnetic field is strong and steady, lacking the violent fluctuations of the solar wind. It is a place of equilibrium. The silence that Voyager found is not just an absence of solar noise. It is a testament to the stability of the deep galaxy. It is a quiet that has likely persisted in this pocket of space for eons, undisturbed until a small plutonium-powered robot from Earth arrived to measure it. This stability, however, hides a tremendous power. The pressure of the interstellar medium is immense. It is the weight of the galaxy pressing down on our bubble. If the sun were to weaken, if the solar wind were to falter, this cold, dense gas would push the boundary inward, shrinking the heliosphere. The fact that the boundary exists where it does 4 times the distance of Neptune is a measure of the balance between the explosive power of our star and the compressive weight of this cosmic ocean. Voyager is now measuring the strength of the opposition. It is feeling the grip of the galaxy, a grip that holds our entire solar system in a pressurized embrace. The composition of this medium also carries a distinct magnetic flavor. The magnetic field lines in the interstellar space are draped over the heliosphere, like water flowing over a submerged stone. As the sun moves through the cloud, its magnetic bubble pushes against the galactic magnetic field. Voyager has provided the first in situ measurements of how these two great magnetic systems interact. It has shown us that the magnetic field outside is stronger and smoother than we anticipated. It suggests that the local interstellar cloud is highly magnetized, a factor that helps hold the cloud together against the vacuum of the wider local bubble in which it sits. We are therefore analyzing the very fabric of the Milky Way. Every atom striking the hull of the spacecraft now is a traveler from the deep past. Some of these hydrogen atoms may have been forged in the Big Bang, untouched for 13 billion years. Others, the heavier elements, were forged in the cores of blue giant stars that lived fast and died young when the galaxy was in its infancy. They have drifted across thousands of light years, pushed by stellar winds and supernova shocks, only to end their journey by colliding with a metal dish launched from Florida. From the vantage point of the interstellar medium, our home looks fundamentally different. For centuries, we have drawn the solar system as a series of concentric rings of flat, static disk like a dinner plate, with the planets marching in orderly circles around a central lamp. This is the internal view, the map drawn by someone standing on the deck of the ship. But from the outside, deep in the galactic ocean, the solar system does not look like a plate. It looks like a bullet. We are not stationary. Disarmed and all, the planets tethered to it are tearing through the galaxy at a velocity of roughly 720,000 kilometers per hour. We are a projectile fired from the spiral arm of the Milky Way, plunging through the gas and dust of the local interstellar cloud. From this external perspective, the heliosphere reveals its true nature. It is not just a container. It is awake. It is the disturbance created by the passage of a star through a resisting medium. For decades, the scientific consensus held a specific image of this disturbance. Textbooks and encyclopedias depicted the heliosphere as a comet-like structure. In this classic model, the nose of the heliosphere, the direction in which the sun is moving, was blunt and rounded, compressed by the oncoming galactic wind. Behind the sun, the tail was thought to trail off for hundreds of billions of cliffs, a long, ragged streamer of solar plasma, left behind like the exhaust of a jet. We assumed our magnetic bubble was stretched thin, deformed by the speed of our passage. However, the data returned from the edge has complicated this picture. Voyager 1 did not exit the solar system in the tail. It exited in the nose, the northern hemisphere of the leading edge. By measuring the pressure and the magnetic field strength at this specific point, the spacecraft acted as a surveyor's stake, pinning down the geometry of the front wall. What it found suggests that the comet model may be too simple. The interaction is far more dominated by magnetic fields than by simple aerodynamics. The magnetic field lines of the galaxy are strong enough to constrain the sun's outflow, pushing back against the tail and shaping the bubble into something more compact. Current models, informed by Voyager's pressure readings, propose a shape that is less like a long-tailed comet and more like a croissant or a distorted sphere. The solar wind, rather than streaming endlessly behind us, is confined by the external magnetic pressure. It splits into two lobes, curving around the sides of the system. This revelation transforms our understanding of the sun's footprint. We are not dragging a long, messy tail through the galaxy. We are encased in a tight, magnetically sculpted pod. The bubble is efficient, self-contained, and remarkably stable, a testament to the intense magnetic forces that govern the structure of deep space. This structural integrity is defined by the bow shock, or, as we have learned, the lack thereof. For a long time, physicists believed the sun was moving fast enough relative to the interstellar cloud to create a sonic boom, a sharp, violent shockwave ahead of the heliosphere, where the interstellar gas would pile up and heat up instantly. This is what happens ahead of a supersonic jet or a bullet. We expected Voyager to detect the turbulence associated with this shock in the distance, but the silence suggests otherwise. The data indicates that the sun is moving through the cloud at a speed that is technically transonic or submagnetisonic. The interstellar medium is not crashing into us, it is flowing around us. Instead of a sharp, violent shockwave, there is likely a bow wave, a gentler, broader pileup of material, similar to the wave that builds up ahead of the bow of a slow-moving cargo ship. The galaxy sees us coming. The pressure wave communicates the sun's arrival ahead of time, allowing the interstellar gas to pass smoothly and flow around the edges of the heliosphere. This discovery paints a picture of a much calmer interaction, where you're not smashing through the galaxy, we are parting it. This God's eye view also clarifies the scale of our protection. When we look at the heliosphere from the outside, we see it for what it truly is, a shield. The interstellar medium is filled with cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light. These are the shrapnel of the universe, ejected from supernova and black holes. They carry enough energy to shred DNA and strip away planetary atmospheres. In the open space of the galaxy, the flux of these particles is intense. It is a harsh, radioactive rain that never stops. The heliosphere acts as a massive force field against this rain. As the galactic wind flows over the surface of the bubble, it carries the majority of these deadly particles with it, deflecting them away from the inner solar system. The magnetic wall that Voyager crossed is the primary deflection point. It is a physical barrier where the magnetic field intensity jumps, acting like a mirror that bounces cosmic rays back into the dark. Without this bubble, the radiation environment on Earth would be roughly 4 times more intense. The evolution of life on our planet, and perhaps our very existence, is owed to the structural integrity of this invisible shell. The silence that Voyager detected upon crossing the threshold is, in reality, the sound of this heavy, radiative ocean pressing against the hull. The pressure outside is immense. We are accustomed to thinking of the sun as the dominant force, but from the outside, the sun appears as a small, pressurized point, pushing back against the crushing weight of the entire galaxy. The equilibrium is delicate. If the sun were to enter a region of the galaxy where the interstellar cloud was denser, a thick nebula, for instance, the external pressure would increase, the bubble would shrink, the heliopause would move inward, past the orbit of Pluto, past Neptune, perhaps even collapsing down to the orbit of Jupiter. In such a scenario, the outside would come inside, the cosmic ray shield would weaken, and the interstellar gas would flood the system. By mapping the current boundaries, Voyager has shown us that we are currently living in a fortunate epoch. We are sailing through a relatively thin, tenuous cloud that allows our bubble to remain large and robust. We are in a clear patch of the galactic weather. The spacecraft's journey has essentially measured the thickness of the hull, reassuring us that, for now, the ship is watertight. The view from the outside also recontextualizes the planets. Inside the system, Jupiter and Saturn seem like titans, massive gravitational overlords that dominate their neighborhoods. But from the perspective of the heliopause, the planets are invisible specks huddled close to the central fire. The scale of the heliosphere is so vast that the distance from Earth to the Sun is less than 1% of the distance to the edge. The entire planetary dance, the history of every civilization, the orbit of every moon, all of it takes place in the deep, hot core of the bubble. To an observer in the interstellar medium, the solar system is not a collection of worlds. It is a singular, unified object. It is a star wrapped in a blanket of plasma, glowing faintly in the radio spectrum, drifting quietly through the dark. This unified perspective is perhaps the most profound legacy of the mission. We sent a machine to explore the parts of the moons, the rings, the magnetic fields, but, in doing so, we revealed the whole. We defined the organism. We now know where the body of the Sun ends and where the rest of the universe begins. We have drawn a circumference around our existence. The data from Voyager allows us to step outside of our own house and look at it from the street, seeing it not as the center of the universe, but as a small, warm shelter with a specific shape, a specific size, and a specific fragility. The voice of the explorer is growing quiet. For nearly half a century, the Voyager spacecraft has maintained a continuous conversation with its creators, sending back a stream of binary code that narrates the story of the outer dark. But this conversation is powered by a finite resource. The heart of the machine is a canister of plutonium-238, a radioactive isotope that generates heat as it decays. This process is governed by the immutable laws of physics. The plutonium does not care about the mission, the data, or the sentimental attachment of the human species. It simply obeys its half-life. Every year, the heat generated by the isotope decreases by a fraction of a percent, and with it, the electrical output available to run the ship. We are witnessing the slow, inevitable heat death of the machine, a long fade that mirrors the cooling of the universe itself. His energy crisis has forced a slow, deliberate dismantling of the spacecraft's functions. The process began years ago, a careful surgical procedure conducted across billions of kilometers. To keep the transmitter alive, the engineers have had to sacrifice the body to save the voice. The heaters that once kept the propellant lines and the instrument bays warm have been turned off. The ultraviolet spectrometer, which once analyzed the atmospheres of Jupiter and Saturn, has been silenced. The planetary radio astronomy instrument has been deactivated. With every system that is powered down, the spacecraft grows colder, its internal temperature dropping closer to the ambient chill of the interstellar medium. The machine is contracting, focusing its remaining life force into the single, essential task of pointing its antenna at Earth. We are now approaching the final threshold of this triage. In the coming years, the power output will drop below the minimum required to operate even the most critical systems. The science team will be forced to make the ultimate choices. They'll have to decide which of the final ears to deafen. Should they turn off the cosmic ray detector to keep the magnetometer running for another month? Should they sacrifice the plasma wave instrument to squeeze out a few more weeks of telemetry? It is a countdown to a predetermined silence. Sometime in the late 2020s or early 2030s, the voltage will drop below the level needed to power the transmitter's amplifier. The Huygens antenna, which has held its lock on Earth for decades, will no longer have the strength to send its signal across the void. There will be a specific moment when the last packet of data arrives. It will travel for 22 hours, crossing the heliopause and the scattered debris of the Kuiper belt, passing the gas giants and the inner planets, until it washes over the dishes of the deep space network. The computers will decode the frame, store the numbers, and wait for the next one. But the next one will not come. The screens will show only the background static of the universe. The link will be broken. The point of light that we have tracked against the stars for 50 years will vanish from our electronic reality. To the listeners on Earth, the mission will be over. But for Voyager, nothing will have changed. The silence of the transmitter does not mean the death of the object. In the vacuum of interstellar space, death is a biological concept, not a physical one. When the electricity fails, the spacecraft does not stop. It merely ceases to speak. It becomes a passive object, a collection of aluminum, copper, gold, and silicon drifting on a dark tide. The laws of motion that carried it out of the solar system will continue to operate with absolute indifference to the state of its electronics. Isaac Newton's first law of motion dictates that an object in motion will remain in motion unless acted upon by an external force. Out here, in the deep gap between the stars, there are no external forces. There is no air resistance to slow it down, no friction to wear it away, no gravity strong enough to pull it off course. The shutdown of the spacecraft transforms it from a robot into a relic. As the heat finally dissipates from the chassis, the entire structure will freeze. The fuel in the lines will turn to solid ice. The metal will contract, settling into a thermal equilibrium with the environment, hovering just a few degrees above absolute zero. In this deep freeze, the process of decay essentially stops. On Earth, artifacts are destroyed by wind, rain, oxidation, and biology. Iron rusts, plastic degrades, stone erodes, but in the interstellar medium, these destructive forces are absent. There is no oxygen to rust the bolts. There is no water to swell the components. There are no microbes to eat the insulation. Voyager 1 will enter a state of perfect preservation. That gold-plated record cover, the etched diagrams, the rivets on the bus, they will remain exactly as they are today. The machine will look pristine, gleaming in the starlight, as if it had just left the assembly line at Jet Propulsion Laboratory. It will become a diamond in the dark, an unchanging facet of the galaxy. If a traveler were to stumble upon it, a million years from now, they would find it frozen in time, a ghost from the 20th century, drifting in the silence. The scratches on the main dish, earned during the launch sequence in 1977, will still be there. The fingerprints of the engineers who tightened the final screws will still be preserved on the interior surfaces. Locked in the cold, this physical persistence changes the nature of the mission's legacy. We tend to measure success by data, the gigabytes of images and readings stored in our archives, but the data is fleeting. It is stored on magnetic drives and servers that will eventually fail or be forgotten. The object itself, however, has achieved a kind of immortality. By escaping the solar system, Voyager has escaped the fate of the solar system. It has slipped the bonds of the sun's future. When our star eventually exhausts its hydrogen fuel and swells into a red giant, consuming Mercury, Venus, and perhaps the Earth, Voyager will be far beyond the reach of that destruction. It will be safe in the cold harbor of the void, unaware that the world that built it has been incinerated. The trajectory of the dead spacecraft is a journey into deep time. It is currently moving toward the constellation Ophiuchus. In roughly 40,000 years, it will pass within 1.6 light-years of the Starglaze 445. This is a blink of an eye in cosmic terms. To Voyager, 40,000 years is nothing. It is merely a span of distance to be crossed in silence. The craft will swing past that star and continue, banking around the center of the Milky Way. Caught in the gravitational current of the galaxy, it will orbit the galactic core just as the stars do, completing a revolution every 225 million years. We must shift our perception of time to understand this future. Civilizations rise and fall in the span of a few thousand years. Species evolve and go extinct in the span of a few million. But Voyager is now operating on a geological, even cosmological, timescale. It has joined the population of asteroids and comets, the silent wanderers that exist for eons. Long after the English language is forgotten, long after the concept of the United States or NASA has dissolved into the haze of history, the craft will still be there. It will be a small, silent monument to a moment when a species of primates learned to build a machine that could outrun the gravity of their home. The silence that Voyager found at the edge of the Heliosphere is now the silence that will envelop it forever. It is no longer an intruder in the quiet. It has become part of it. The distinction between the observer and the environment has collapsed. The probe is now just another rock in the stream, albeit a rock that has been shaped by intelligence and imbued with a memory. It carries a secret cargo, a message intended for no one in particular, a shout into the void that has been frozen into a whisper.